We know how terrifying and powerful black holes can be, but what comes second place in terms of overall awesomeness? Join us today as we learn about neutron stars. One of the most popular outer space entities that pop culture love to revolve about is the black hole. We've seen various movies, TV programs, even some songs talk about how magnificent and mysterious they are. But what if black holes aren't the only objects that we should be amazed with? Of course, we have a lot of picks for that matter, but the particular thing we could talk about today is the star that ranks number one in the universe in terms of density, the neutron star. Okay, astro fans, I could hear you argue and say, no, black holes are the densest objects in the universe. But let me tell you this, remember how black holes work? They are effectively stars that collapse to an almost zero volume, which results in their enormous gravitational force. If they effectively are dimensionless, can we really say that they are objects? We can't be really sure, and that's something that only philosophy can answer. But while we're here at the subject of definitions and what we actually know for certain, let's just say the one we can categorize as the densest object, quote unquote, is the neutron star. And no, a neutron star is not a subatomic particle which grew to the size of the star. It isn't also a bunch of neutrons agreeing to somehow collectively come together to form a humongous star, although we can effectively say that a neutron star is like a giant atom. We'll get to that later. For now, I want to discuss how neutron stars are born and why they are like phoenixes, how from the ashes of their old corpses, they rise up and fly with their new, replenished lives. I know you already know this if you're an astro buff, but to some of our viewers out there who are new, first of all, welcome. We hope we spark your curiosity more through our videos. Anyway, stars were discovered to follow some kind of life cycle, just like us living beings on Earth. They too get born, have a childhood phase, then grow to adulthood, then also die after certain circumstances. A star's usual routine involves fusing hydrogen into helium. Quite honestly, in its lifetime, that's all it ever does. Now, as we know from basic nuclear physics, when we fuse atoms together, it creates energy. The energy that the fusion in the star creates is countered by the gravitational force towards its center, effectively keeping the balance and preventing it from collapsing towards its center. As long as this goes on, everything is good and well in a star's life. But of course, like all lives, stars experience a tipping point in theirs. Remember how stars burn hydrogen to fuse to helium? Well, eventually stars run out of hydrogen to fuse, so they fuse helium instead, forming elements such as carbon and oxygen. The energy pushes out the borders of the star, causing it to move to its giant phase, until the pressure from electron degeneracy collapses the core of the star and expelling its outer layer, leaving a white dwarf. For heavy mass stars, a number of times larger than the mass of our own sun, the story is different. The same as earlier, when the star runs out of oxygen to fuse, it begins to fuse heavier elements. The difference this time is that the collapse caused by gravity is so extremely strong, way stronger than what we described earlier, that the fusion goes to neon, to oxygen, to silicon, then finally to iron. As this happens, the outer layer of the star begins to fatten up faster as time goes by. When the core of the star is finally iron, fusion can no longer take place, as iron is stubborn this way. We can imagine at this point there is no more energy resulting from fusion. So what if that happens? The very own weight of the star collapses in itself, effectively crushing it to the size of up to around a 10-kilometer radius. It's like compressing the star to about the size of Malta. Now we know how subatomic particles don't want to get near each other, right? We can practically say that an atom is made of empty space. However, the strength of the gravitational force that occurs when a heavy mass star collapses crushes this space in between, merging the protons and electrons together to form neutrons, with some neutrinos in excess. But the extravaganza of energy doesn't end there. See, neutrons hate being compressed towards one another too, just like protons and electrons. The collapse can only occur up to a certain moment where the neutrons form a lattice-like structure. The crushing in stops. By the way, this sudden halt is what we call neutron degeneracy pressure. The energy from this event results in a massive supernova, outshining anything else in the galaxy. What's left behind is a cloud of plasma. From the ashes of the former star rises the old core, now what we call a neutron star, the most dense object in the universe, after the black hole. I hope you still remember the thought earlier whether we can call a black hole an object or not. What do you guys think? Can black holes be considered as objects? Leave us an answer in the comment section down below. You may be wondering just how dense these neutron stars are and why they are the next most extreme objects in the universe after a black hole. Well, to put things in perspective, let's say for some reason you can acquire a part of a neutron star about the size of a sugar cube. That small chunk you have in your hand contains the mass of all the living humans on Earth. Imagine how sweet that would make your coffee, or tea if you're British. Okay, let's carry on detailing more about our stellar phoenix, shall we? The density of a neutron star is tremendously large. In fact, if it were to become a bit denser than it already is, the gravitational force would again tip the scales and collapse it to a black hole. Due to the same reason, it can also cause ripples in space-time and bend light around it. The surface of the star is also extremely hot, around 600,000 K to be exact. To put things in perspective, carbon, the most difficult object to turn to gas, will sublimate at around 3,900 K. I think if everything on Earth is to be placed on the surface of a neutron star, we would instantly vanish. That is, if the strong gravity doesn't tear us up to pieces first. Now that's hardcore. But okay, a neutron star is the core of another star. But if we have a hypothetical astronomical surgical knife strong enough to cut it open, what things are we bound to find inside? Surprisingly, it is said that we are bound to find planet-like characteristics inside neutron stars. Firstly, after we peel off the hot atmosphere, we're bound to find an iron-hard crust made of, well, iron. Because if you recall earlier, the elements in the star are essentially squeezed tightly to become ferrous. Naturally, it is fair to expect the crust to be like this. Now, as we drill deeper into the star, we are bound to see just how tightly gravity compressed the parts of the old star together. In the next level of the crust, we are bound to see a few atoms clumped together, forming what looks like oval-shaped lumps. Because of how it's hypothesized to look, scientists called this the gnocchi phase. As we go deeper, the gnocchis of atoms are now crushed further in long rod-like fashion, forming the spaghetti phase. Finally, at the last place before the core, the nuclei are now expected to form a flat layer, forming the last variety of pasta in our example, the lasagna phase. And collectively, these layers of deliciousness, of the neutron star's crust, from what scientists call, surprise surprise, nuclear pasta, the most unbreakable material in the universe, at least in theory. Okay, now that we're done being hungry because of all of that pasta talk, let's move on to what could be in the core of a neutron star. Well, at this point, scientists run out of pasta to describe what goes on. Not because there isn't any more comparison, but because no one knows for sure what it's going to be made of. Some thought that the nucleons break down into strange quarks, forming a sea of strange matter. Some infer that the protons and neutrons retain their forms and just swim about in this extra dense pool of energy and mass. But whatever it is, I think we can all agree that it is something worth looking forward to, especially if it's going to be analogous to another pasta variety. It's common knowledge in astrophysics that stars exhibit some kind of orbital motion, and when an object rotates, it exhibits angular momentum. The neutron star, being part of an older, already spinning star, inherits this characteristic. But before I discuss that any further, let's take a bit of a stroll to watch a skater perform a spin. When the skater's arms are widely spread, she spins at a really slow pace. However, when she draws her arms closer to her body, she begins to spin faster. From that visualization, we can notice that objects spin faster when they have a shorter radius. Okay, back to the neutron star. From being a supergiant to having a diameter about the size of a regular city, we can imagine how drastic the change in radius is, and therefore the change in angular speed. A neutron star has to be spinning really fast, as much as multiple times per second. Moreover, it's not just the rotational speed of the star that received a boost. The magnetic field does as well. Just how strong was the increase, you ask? Well, let's say a neutron star suddenly popped into existence about halfway from the Moon to the Earth. The magnetic field exhibited by that neutron star is enough to erase all the credit card information here on the planet. The ultimate hacker. Scientists initially doubted the existence of these objects until it was verified by a graduate student named Jocelyn Bell in 1967. At the time when she was helping build a telescope and discovered certain noises from their observations, which as it turned out apparently were actually pulsars. If you're creative enough, it's easy to deduce that the name pulsar came from the combination of the terms pulse and star, which is exactly the nature of these objects. A pulsar is a neutron star spinning with a speed so fast and a magnetic field so strong that beams of light come out from the poles of this star. This is what caused the noises that Bell observed in her data. The telescope recorded periodic flashes of light akin to a pulse, which turns out to be one beam of light approaching the Earth from a neutron star light years away. It's like a nonsensical intergalactic Morse code. Now, there are moments where the magnetic field increase in a neutron star can set to hyperdrive, even going as much as about 10 to 15 times stronger than the Sun's own magnetic field. These objects are named magnetars. Although this feature causes this neutron star to slow down its own spin, it's still a force not to be reckoned with. When a magnetar releases its own stellar flare, it could be felt billions of kilometers away. In 2004, a satellite named Swift, built specifically to detect powerful X-ray sources, momentarily went offline despite not pointing to anywhere in particular to measure X-ray magnitude. Turns out the burst felt by the satellite came from a magnetar about 50,000 light-years away from the Earth. It also briefly messed with our own magnetosphere and partially ionized the upper atmosphere. Imagine just how strong that energy is to cause a detectable effect to us, even though we're literally as far as we can be from it. But despite the level of unimaginable strength this type of neutron star has, they're an extremely rare breed in the galaxy. Scientists estimate that there might be just over a dozen magnetars in the whole universe, at least in the whole observable universe. Moreover, since they are relatively few in number, the catastrophic effect of a magnetar burst can be rarer. I mean, we practically already have the technology dedicated to detecting and studying these types of stars. If they occur as often as we initially thought they would have picked up something already at this point. I bet at this point you're pretty amazed by how fascinating neutron stars can get. We thought the flat earthers are the densest items in the whole universe, but today we learned differently and discovered that even they fail to even remotely match the density and the level of awesomeness that the neutron star carries.